Okay, the point is whenever you have a general region for triple integrals written the way where your region is an inequality with a above surface and a bottom surface. So in this case, we have a function that's described by 2 times x times y and the missing z variable. So it's constant for whatever z variable you're looking at. And we're integrating over the region E, whose region we found in the previous problem. That is this sort of acorn region. And we described its limit of integration. We described its region with the following inequality. The strategy is first you want to write your region into an inequality that expresses your first variable as a function of 2 other variables, so a top surface and a bottom surface. Your next variable, in this case we had worked with y, as being a function, or 2 curves, a top curve and a bottom curve, relative in this case to the y direction, as a function of x, and the last variable, x, or integrand, as a function, as a number, a and b, or top number and bottom number. We were able to do this, and note that R2 is just this number. I just don't want to keep writing the square root mess or deal with the approximation, so I'm keeping it as R2 as I evaluate this expression. We plug in our function into the triple integral, we plug in our limits of integration into the triple integral, and then we do the regular kind of integral thing with the idea that we do the integrand, the innermost integrand first and work our way out. If we're integrating with respect to dz first, all other variables are considered constants. That's why I factored out these variables, the y variable and the x variable, and the 2 as if they were constants respective to the integrals they were seeing. So the y comes all the way outside of the dz integral. It doesn't go past the dy integral because now that's a variable for y. The x gets factored out to past the dy variable because it won't be a variable until you hit the dx level. And the 2 is always a constant, so it goes all the way out. The first integral is easy because it's just the integral with respect to z of constant 1, which is just a z. You evaluate the limits of integration in the following way, which I put over here and over here. dz is done, and we're on to dy. Now, dy takes a little bit more work, but if you look at this particular mess of integral here, there are 2 parts. The -1 plus 1 cancels out, so that simplifies things a bit. The y can be distributed to each of these terms, but at least the term of the x squared and the y squared are going to be the regular power rule. So we don't have to do anything special to them. So I'm going to use the integral properties that says if you can find the integral of 2 different functions being added together, you can just add their integrals. So I break it apart into these 2 pieces. I do that because I'm going to have to use a u substitution for this one. In this case, my variable is considered y, so I don't have to worry about this x, but this is the square root of a y squared inside of here with a y on the outside. In that case, a good u substitution would be to replace all the stuff inside the square root with just a u. Then I use this standard trick of taking the derivative of both sides of this expression to tell me that my du equals negative 2y dy. Don't forget to write your differentials when you're trying to do u substitution. I go ahead and divide the negative 2 into both sides of the equation. This should actually be a negative right here. It's okay. I'll fix it later. And then I do substitution, so I have a simplified integral that I could just use the power rule on. And for this bottom integral, it's straightforward. Just use power rule, which is what you see here, relative to the y variable. I noticed I forgot to write the 2 here, the 2 here. I also forgot to carry the negative sign from one of the previous steps all the way down. Oh, sorry, this negative sign. There should be a negative sign written right here. That negative sign would have come from the U2. I'll come back and fix it later. But then I evaluate my limits of integration, since my y is done for both of these. Remember to replace your u with what you said over here, the 16 minus x squared minus 2. Then I can substitute this everywhere I see with a y, which is what it looks like over here. This is a slight error. There should be a plus sign, so that's a mistake. But even so, I have a square outside, so when I square this expression and I square this expression, they look exactly the same. No matter how this reduces, and it does reduce, what I have is one expression right here that looks exactly the same as this expression over here, and they cancel out because I'm adding and subtracting the exact same thing. Similarly, when I look over here, I have an expression here that cancels out one expression here with the even power. So this is fine, my limited regression. Here I have the negative in front of the same square root because that's a lower curve. But I have an even power, so the negative gets canceled out here, the negative gets canceled out here, and the result is an expression that is opposite signs but the same expression, so it cancels out, becomes 0. In effect, by the time I get to my x integral, I have 0. I'm integrating the 0 function for both of these. This should be dx. The integral of 0 is always 0 for a definite integral. So both of these integrals are going to be 0. That tells us that the integral of this particular function over this region is 0. What this is telling you is that if you're totaling up the values of your function, it should equal 0. There are properties from Calculus 1 that you could use to have made this problem faster. One of the properties is the idea of odd functions and even functions over regions that are symmetric, so this just as much below as above. For an odd function, that always equals 0 because you're adding the same negative number to the same positive number. For a even function, you only have to integrate halfway from 0 to the top curve, or from 0 to the top surface, or from 0 to the last number. That's your limit of integration, and that will equal 2 times whatever integral that you had. If you look at the solid graph, which I tried drawing over here, this red curve is supposed to be the level curve for the function we're integrating on the inside. So only parts of the red curve within the code region we have here are being computed as a factor in the volume. So this red surface going this way, that's my function value whose outputs, these are all the x, y, z coordinate pairs whose outputs are equal to -1. You can try to think of it, the part of the surface that goes through our integration region, they all have the same value. They have this sort of like weird bend shape. They have a slice by the acorn, so they have like a little parabola slice inside of it. And it's the same one on the other side. If I take that negative sign, I just switch it to a positive, I get exactly the same shape with the exact opposite output value, a +1. So you can think of it as being the same amount of material or area that's being canceled out when I multiply the volume function and add it to the other area, the -1. And if you play with this a little bit, you can see for every choice, and I'll just put in simple numbers, if I put in 2, you can see that I get exactly the same shape as if I plug in -2. So I have not defined what it means to be an odd function, what it means for my function to be odd function over symmetric area. This is something we can mathematically define precisely, but intuitively it has the same idea that for every negative number where I can evaluate the integral for my function as an output, I have exactly the same amount of region, different region, but same amount of region, same area for the positive number. When I do these multiplications, they cancel out because of symmetry, rotational symmetry. It looks the same no matter how I rotate it around the axes, so it cancels out everywhere. We don't really introduce those properties in this textbook, but those properties exist, and we could see them in other textbooks, or you could derive them in later math classes.